Welcome to our explainer, where today we're tackling a force that's all around us but totally invisible: adhesion. It's the reason that fine dust seems to have this super-powered, stubborn grip on pretty much every surface.
I mean, think about it, right? You can shake a towel and the sand flies right off. But that thin layer of dust on your TV screen, you can't just blow it away. It seems like it should be simple, but anyone who's ever tried to get a surface perfectly, truly clean knows there's a lot more going on here than just gravity.
And that's the thing. For these tiny little particles, gravity is, well, it's almost irrelevant. They live in a world that's run by these powerful adhesive forces that are literally orders of magnitude stronger than anything we're used to. The rules of physics are just different at this scale.
So how are we going to break this all down? Well, first we're going to look at the nature of this unseen sticky force. Then we'll get into the three main forces that actually create it. After that, we'll figure out what it takes to break that bond, how particles get kicked back up into the air, and why sometimes they just bounce right off. And finally, we'll wrap it all up by looking at why any of this really matters.
Okay, let's start with the absolute core idea here. Aerosol particles don't just land on a surface, they attach to it, and they attach firmly. This isn't some casual thing, it's a defining feature that separates them from bigger objects. This is absolutely fundamental to everything that follows. And this quote just hits the nail on the head. It's the whole challenge in a nutshell. What it's telling us is that when you get down to the micro scale, adhesion isn't just one of the forces at play, it's the force. It's the boss. Everything else, like gravity, it's pretty much just background noise.
So, where does this incredible grip actually come from? What's the source of all the stickiness? Well, we can actually break down the physics of it into three main types of adhesive forces.
And here they are, the big three: van der Waals, electrostatic, and surface tension. If you want to really master this topic, you have to understand how each of these works. So let's take them one by one. All right, first up, van der Waals forces. The easiest way to think about this is to imagine that every atom has this cloud of electrons buzzing around. As they move, they might momentarily clump on one side, creating a tiny, temporary magnet. That little magnet then causes a temporary magnet to form in a nearby surface, and click, they're attracted. This happens everywhere, but the catch is it's a very short-range force.
Next up, electrostatic forces. Now, most tiny particles have a little bit of a net electric charge, so when that charged particle gets close to a surface, it's like bringing a magnet near a bunch of paper clips. It makes the charges in the surface rearrange, creating an opposite charge right there on the surface that pulls the particle in. This one's a really big deal for insulating materials or when the air is dry, because the particle can hold its charge for a long, long time.
And finally, we have surface tension. Now, unless you're in a perfectly dry environment, pretty much every surface has this super thin, invisible layer of water on it. When a particle lands, that water gets sucked into the tiny little gap between the particle and the surface. And this creates a little liquid bridge. And the surface tension of that water acts like a super strong microscopic glue, just pulling the two together. Okay, this is a huge point. This is the insight that connects all three of those forces. For all of them, the strength of the adhesion is basically proportional to the particle's diameter. It's a simple, linear relationship. So if you double the diameter of the particle, you roughly double its stickiness. Remember that simple rule, because it's about to become very important.
See, understanding the forces holding a particle down is only half the battle. To really get what's going on, you have to look at the other side of the coin, the forces that are trying to lift it off. And this sets up a fascinating tug-of-war.
And here it is. This is the whole conflict laid bare. We just said that the sticky forces scale with the particle's diameter, to the first power. But look at the removal forces, things like air currents or gravity. They scale with the square of the diameter, or even the cube. This massive mismatch in how the forces scale with size, that is the entire reason small particles are so ridiculously hard to remove.
This table, this is where it all clicks. Just look at that top row for a tiny 1 micrometer particle. The adhesion force is about 10 to the minus 7 newtons. Now look at gravity. It's 10 to the minus 15. That's 100 million times weaker. Even a really strong gust of wind is still hundreds of times weaker than the force holding that particle down. It's not even a fair fight. Adhesion wins by a total knockout.
So what's the bottom line here? The key takeaway? As soon as a particle gets smaller than about 10 micrometers, the forces trying to pull it off become almost laughably small compared to the forces gluing it down. It gets exponentially harder to remove them.
Okay,
So we know it's incredibly hard to detach these particles, but it does happen. So let's look at how they actually manage to get airborne again. The technical term for this is resuspension.
Now here's a really important distinction. You can't just blow on a surface with a steady stream of air. See, most particles are hunkered down in this very thin, very calm layer of air right against the surface, called the laminar sublayer. They're protected. To get them out, you need a sudden, violent burst of turbulence, an eddy, to punch through that calm layer and basically flick the particle out. This means resuspension isn't a steady process, it's random and chaotic.
But what about the complete opposite? What happens when a particle hits a surface and just doesn't stick at all? This is the really interesting phenomenon we call particle bounce. Really, it all comes down to a simple battle of energy. The particle smacks into the surface carrying kinetic energy. The surface tries to absorb that energy and form that sticky bond. But if the particle has enough energy left over to rebound with more force than the adhesion force can supply, it's just going to bounce right off.
And this slide just lays out the rules of the game perfectly. So what makes things stick? Slow speeds and soft, mushy materials. Think of a tiny speck of soot gently landing on a greasy surface. And what makes things bounce? High speeds and hard materials, like a tiny, solid glass bead hitting a steel plate.
Okay, so we've dug into the physics of sticking, detaching, and bouncing. But let's be honest, this isn't just a science experiment. Why does this stuff actually matter out there in the real world?
Well, it turns out these principles are everywhere. I mean, they're absolutely critical for designing good air filters, for figuring out how dust builds up in our HVAC systems, for controlling dust on dirt roads, even for making sure scientific instruments work correctly. From modeling how soil erodes to manufacturing medicines, it all comes back to the fundamental concepts of adhesion we've just talked about.
So, let's end with a challenge for you. Now that you know the rules of the game, how would you flip them? How would you design a surface? What material would it be? What texture would it have? To create the ultimate non-stick surface for the microscopic world. Something to think about.